much. Good morning to everyone. It's a big pleasure to be here. I'm Niccolo Somaschi, CTO, and I'm here with Shane Mansfield, Chief Research Officer. Today we're going to present you our effort in Quandela, providing quantum computing solution based on photonics. A few words about the company. Now 70 people across different field and expertise. We founded in 2017, and we are based mostly in Paris area, where we have access to different facilities for prototyping and assembly of quantum computing platform, but also to develop and push the technology on the semiconductor side with access to a research clean room facility, and towards the end of the year, having our own clean room for A to Z production of these photonic devices. What we fabricate is here. You can see it. You can see it also in our booth. It's a server rack size photonic quantum computer built up by different modules from the hardware up to the middleware, compilation, operating system, all internally developed, our own framework and programming language, up to the access to the cloud. And why we do this? We do it for delivering this photonic quantum computing machine on-premise, which are prepared and assembled to be connected effectively with a classical machine in HPC data center with CPUs and GPUs. We also provide service and co-development of tailored algorithms for industrial use cases. We do this with our partners and clients. We also develop our own programming language to access our photonic quantum processor. It's called Perceval, and we are very engaged with the community, make this available and make photonic quantum computing available and understood by a larger community as possible, also partner in the academic side. And of course, we provide access to quantum processing unit via cloud service. A few words about the technology. Let's zoom out a second and look at the different approaches to build up quantum computers. We can take matter-based qubit, ions or superconductors, which are fabricated on a processor and sits at the bottom of a dilution fridge, or atoms which are placed in ultra-high vacuum. And these objects, they are visible. We can see them, and we can place them one next to each other and perform logic gates among them. But towards the development of thousands and millions of qubits, the manufacturability becomes a problem, because we have to fabricate on the processor millions of qubits, and because we have to be able to connect it. And connectivity is now understood as the most efficient way to enlarge the computing power of this platform. On the other side, we have photonic qubits, which are flying object. They don't sit on a processor. The processor itself is classical. It can be made of integrated photonic circuit or loops of fiber and such. And therefore, we need to be able to generate efficiently the photonic qubit, manipulate them, and detect it. These are the three building blocks. So the manufacturability, when we take and we leverage telecom industry, it's providing a long way to the required development. What is important, though, what's hard in this case, is to make and generate entanglement in between photonic qubits. This happens with a certain probability, and this is pushing back the scalability of this system. What we do in Quandela is to tackle the generation of photonic qubits and generating entanglement among them with a matter-based qubit. It's a nanostructure with a spin qubit, which permits to generate efficiently entangled photonic qubits in a stream. And after this tough part, which is done on demand, we can then leverage linear optics, photonic integrated circuits, and fiber and switches to manipulate this object, and therefore scale to the required number for useful machines. So the main blocks, you can see them here: generation, manipulation, and measurement. We have to make them efficiently. Photons are resilient to the coherence, but we have to keep them. We don't have to lose them. So the efficiency of these objects is crucial. And then, of course, we have all the electronics required to manipulate them. So the computation works that by sending photons from one side, we manipulate them, we detect them on the other side. And each shot defines results of an algorithm. So we can run them very fast because you know photons travels at the speed of light. What we do on the development towards error correction is by taking step by step and providing machines which increase number of qubits by time. We want to make these steps, making a platform of tens of qubits available on the cloud, develop with the community algorithms which can be tailored to specific use case, it can provide an advantage, and push towards more complex, higher number of qubits, developing algorithms which have broader use and also an advantage for real-world cases. On the technology side, we will move from current manipulation of single photon into the manipulation of cluster state by using the same core engine. This quantum light emitter that is generating single photon and entangled photons on demand. And this is something we have already working in our laboratory. So we look in the longer term, the machine will work in this way. You have always this generator that instead of producing stream of single photon will produce stream of linear cluster state of photons. And the manipulation will allow the weaving of this linear cluster state to generate 2D graph that evolves in time and where the computation will be encoded. It will be encoded with error correction protocol and will allow, therefore, an implementation of the use case which the industry is looking for.
Great. Okay, so Niccolo has given you a lovely overview of the technology, and perhaps some of you have already seen the device at our stand. If you haven't, I encourage you to go and see it, because I think it's quite impressive to see a device that's just a little shorter than me and a little wider than me. That's a full integrated quantum computer. But I have good news, so I want to start my part with something for everyone in the audience, in a sense, is the fact that you can access our machines online on the cloud now. And it's an excellent idea to go to cloud.quandela.com and to register for an account. And if you do so now, if you do it this week, you will actually get some free credits. And you can begin to play around yourself and test out photonic QPUs. So what you see if you go to Quandela's cloud, it's everything that you expect. You're going to pick a processor that you can work with. You're going to have some job lists, see what you've sent out, and statistics about your usage, and so on. Now, the point of entry to Quandela's QPUs, it's our open source framework. So that's open source, it's community driven, and it's for photonic quantum computing in particular. So why do we have our own framework? Well, it's because we work with photons, and you need something photon specific to be able to talk about the gates that the photon sees and program them at an appropriate level. Now, if that sounds heady to you and it's something that you're not ready to engage with just yet, I also have good news. You don't really need to engage at the photonic level because everything in Perceval is fully compatible with hardware agnostic approaches. So if you've already been working with some software platforms, if you've been working, for example, with Qiskit and you've written some code and you'd like to run it on a photonic processor, good news, you can do this on Perceval. So we have some connectors that will do some automatic translation. Now, I'll give you the caveat with that. Usually when we work on this with someone, we find better, more optimal ways to do it, but this works very well to get started. So our Perceval software is also, as I said, open source. It's free for everyone to use. There's a lot of documentation that goes with it that can help you to get started. And there's even a scientific paper that gives you some examples of using photonic hardware to solve interesting real-world use cases. So with the growth of the quantum computing community, we increasingly see quantum curious businesses, industry starting to awaken to quantum computing. Maybe it's people who have not already developed a deep expertise of quantum algorithms, but are beginning to dip their toes and build their capacities. And an approach that we found works very well when we work with clients is to provide a toolbox. And so with our toolbox, we are including a number of primitives, and these are solvers for the kinds of problems that people might encounter daily in their own industries. And so for example, what we can do is we can provide a differential equation solver. And so what you need to do is just provide your differential equation and some parameters about how you want to go about solving that. And you don't need to know the detailed under-the-hood workings of our photonic algorithms, which are very optimized for our hardware. Similarly, we have some certification primitives for the generation of certified generation of random numbers. You can solve optimization problems formalized as QBOs. You can solve graph problems, or you can do a variety of quantum machine learning tasks. So these typically are variational algorithms, like the variational quantum eigensolver that sometimes people will talk about for finding ground state energies, for example. And so what I've given on this slide are some illustrative use cases. So they're illustrative only, there's not so much to read into these. These ones all have to do with finance, for example. But what it shows is that someone can come along and they can say, okay, well, you have a differential equation solver. I have this problem that I need to solve, that's important to me, that requires solving differential equations. And that's usually a very good starting point. So these are a bunch of out-of-the-box solutions that are available. Some of them already through Percival and some of them coming through Percival. So for these, as I say, they're out of the box, but our preferred way of working, so I'm going to just quickly jump to that in a moment, but I'm going to just make a point about why we've chosen these particular primitives is because they're very versatile. So we've decided to favor solutions that have broad applicability across industrial sectors. And so an example of that, if you want to take the differential equation solver, we could easily find interesting use cases today in finance or in logistics or in aerospace, all of which relate to solving this. And the same goes for the other primitives, and that's very much at the philosophy, it's very much the philosophy of deciding which primitives we want to work on. Okay, so as I mentioned, these are out-of-the-box solutions, but our preferred way to work with people is actually together. And so for many people, their quantum computing journey is beginning around now. And the message for those in the audience who are dipping their toes is that Quandela can work with you and can support you along the way, providing products and solutions that are really tailored to your needs. And we've been working on this with many partners, and we've kind of got a 5-step approach to this. We like to start by, of course, identifying a problem that's important for you. But then we also like to know that it's something where we can really provide something of interest, where photonic quantum computing in general can do something interesting, something hopefully advantageous. And so we'll work and we'll consult with our science and our applications teams. And we go on to develop models, we'll run some simulations, we'll see that it's working, and then we'll move to the actual quantum devices, where we can do some benchmarking and finally deploy the solution. So that's our preferred way of working. If this is of interest to you, come and talk to us at the stand. So now I'm going to switch slightly. So I'm telling you about how we like to work for use cases, but you might also ask, well, how good are these machines? And we're happy to talk about that because we're quite proud of where we've gotten to. And so what I'm showing on this slide is some benchmarking. Our processors are on the cloud. They're publicly available. And once you're on the cloud, people can already start to benchmark. Now we can look at other processors that are on the cloud and we can see how they compare to each other. Now the idea here is not to give an absolute answer, this processor is the best and this one is the worst. And it's really to start to understand the relative merits. These are things that are evolving fast, and even our numbers are going up weekly in the labs. So what we have on this slide, we have fidelities for single qubit, 2 qubit, and 3 qubit gates. That's shown on the left. We find a particular advantage in our hardware when we move to 3 qubit gates, interestingly. We see favorable comparison across the other free-to-access processors. The other thing that we think is important to keep in the discussion is the speed of operation. So how many operations can you do per second, for example, and typically entangling operations are what are going to be of interest. So that's an interesting trade-off to keep in mind. And is also worth stressing the availability of the processors. So we're proud to say that our processors have an availability of upwards on 95%. And this is really a testament to the very hard work of our technical teams to get the kind of stability required to make it available. And as far as we can see, this is more availability than any of the other processors out there. So that's to tell you about the benchmarking. Here we're talking about qubit gates, and there's a very natural way to start benchmarking. But I mentioned that when we are solving the problems, when we're actually running the primitives, we often have them very optimized for our specific photonic hardware. And so sometimes it can be interesting to go beyond qubit gates, to go to something a little more photon specific, and we can eke out extra performance. And so for this, I'm just going to take a little peek under the hood at how the processors run, which perhaps will be of interest to some of you, many of you, most of you, hopefully. So we have two different kinds of processor, broadly speaking. The first kind is a universal type processor. So a decomposition here that would be familiar to some of the scientists in the audience. It allows us to implement qubit operations. So this would allow us to do our single, 2-qubit, and 3-qubit gates. But it also allows us to run what we call photon native algorithms. And so that means we're not encoding qubits directly. We're treating the photons as the information carrying units by themselves. Examples of this are Quandela's differential equation solver, or many algorithms that are based around a task called boson sampling. And in particular, boson sampling has been in the news because it's what led to some of the demonstrations of quantum computational advantage in the last years. So there can be a great advantage to exploiting that. This is a versatile design, a universal one. And a second kind of design, it's more application specific. And so since we have a modular technology, we can really work with one chip and then just decide to reroute photons to another chip if we want a different kind of functionality. So this particular chip, it's specialized for machine learning. It's good for generating ansatz circuits for quantum machine learning. And it's interesting to work with this because we can optimize. So we reduce the number of parameters on it compared to universal architectures, which allows us to increase things like fidelities and transmissions. We're also, I'll plug some of the tools that we use here to get very optimized photonic designs. We use something called the love calculus, which allows us to simplify the circuits and find the most natural form. So there you have two different kinds of processor, a general kind and an application-specific kind. And there's a short video which just shows how the processors work. So we stimulate our sources to release photons. The photons come out, that's the red wave packets that you see coming out here. Typically, we'll do some linear optical manipulation with them, and that will be on chip. But for the purposes of the illustration here, it's useful to show them in free space. And you can see the components that they're going through. They're actually very familiar things. They're like mirrors and beam splitters. And these purple components are phase shifters, so they just slightly change the state of the photon as it passes through. The photons meet each other, they interfere, and eventually they find their way to our detectors. And off the back of the detectors, we're able to run our quantum algorithms. And so what you see in this image is our differential equation solver converging based on the statistics that it's receiving from the processor. So, as I say, go to cloud.quandela.com. You can access all of this today. And I'm going to close with an image of the 3 available QPUs at the moment. So these are 3 QPUs that are running. The first one is application specific. It works for certification. The second one is 6-qubit. It's fully reconfigurable. So that's a general processor. And the third one is 4-qubit, which is application specific and tailored for quantum machine learning. So this one is not on the cloud yet. It's up and running in the lab, but will shortly be available at cloud.quandela.com. So go and sign up.